Now that we've had a chance to understand functions a little bit, we're going to look at two specific types of functions called injective functions and surjective functions. First thing we're going to do is we're going to define injective functions. We're also going to define what surjective functions are. And then we're going to look at some examples. So I want you to remember that by our definition of functions, every input can have only one output. It has to have an output and it can have only one. So if I have an array like this that claims to be a function, I can look at those two inputs that say 1. Each of those is the same input, but one of them has an output of 2, one of them has an output of 3, so that is not a function. However, even though we can't have one input that has more than one output, we can have two different inputs that give the same output. So we can have one output that has two inputs associated with it. So if we had something like this, where, let's see, we have the input 1 gives us the output 2, and the input 3 also gives us the output 2, that's still a function because each of the individual inputs give us exactly one output. So each input has one output, that means it is a function. However, this does indicate that we might want to distinguish between functions whose outputs are all different and whose functions where some of the outputs are the same for different inputs. So we say a function f from the domain A to the codomain B is injective if there are no two inputs that have the same output. So let's look at an example. Here's a function with inputs, the letters A, B, C, D, and E, and the outputs are going to be real numbers. So the function itself is going to be given by the following array. The inputs are on the top row, the outputs are on the bottom row. And if you look at f of b, that is equal to 5. F of d is also equal to 5. So f is not injective. Here's another example. Same inputs. The outputs are a little bit different. Notice that each output is paired with exactly one input. The output 2 only goes with A. The output 5 only goes with B. The output 3 only goes with C, etc. And that means the function is injective. So another question you might ask about functions is how much of the codomain consists of actual outputs? As we saw in the previous video, it is possible to have a codomain that has lots of elements that aren't outputs of the function. So that inspires this definition. So if f is a function from domain A to codomain B, we say that f is surjective if every element of the codomain B is an output of f. Another way of saying that is that the range of f is equal to the codomain of f. So here's an example of a function f with inputs a, b, c, and d, and possible outputs 2, 5, and 8. If I look at the following function with a, b, c, d on top, and outputs 8, 2, 5, 2 on the bottom, notice that b and d both have an output of 2, so it's not injective. However, notice that f of b equals 2, f of c equals 5, f of a equals 8. Those are all the possible numbers in the codomain, which means every element in the codomain is represented as an output. That means that the function is surjective. Every output is represented as, or every element of the codomain is an output. F is surjective. But if we have something like this, where a goes to 5, b goes to 2, c goes to 2, and d goes to 5, notice that 8 is not an output of that function, even though it is a part of the codomain. Right? So not every element of the codomain is an output, which means that f is not surjective in that case. So now let's look at a function given as a formula, because those tend to be a little bit more tricky. So our example is going to be a function f whose inputs are real numbers and whose outputs are also real numbers. And it's going to be given by f of x equals x squared. Now, every time that you square a number, a real number, you can never get a negative number. So every output is going to be a non-negative number, which means that negative real numbers cannot be outputs of this function. Now, the codomain is the set of all real numbers, which includes the negative real numbers, and that means that f is not surjective, since the negative real numbers in the codomain are not outputs of the function. So as looking at the issue of being injective, being injective, Notice that when we take f of 3, we square 3, you get 3 squared, which is equal to 9, which is fine, right? But also, if you plug in the input -3, if you square -3, the negatives cancel, and that also gives you 9. So what we have here is we have two inputs, 3 and -3, that give us the same output, which means that f is not injective. So that tells you gives you an idea of how to show a function maybe is not surjective or is not injective. It's a little bit more difficult, or a little bit different maybe. Maybe difficult isn't quite the word I'm looking for. To show that a function is injective or is surjective when it has a formula. We've seen, looking at an array, it's easy to tell if it is. You just look at all the inputs, make sure they all have the same, all have different outputs. For injective, you just look at the bottom row, just make sure all the elements of the codomain are represented to see that it's surjective. But when you're dealing with something where the inputs and outputs can have infinitely many elements, that can be a little bit more tricky. Well, you'll get a chance to try that in the in-class activities. Alright, so now I think you're ready to work on the activities for this. It's in the PDF file called Injective and Surjective Functions, and it's included with this video.